So I got this person that's doing some chores. Looks like they're loading up the back of a pickup truck, and they've got a 5 kilogram box. So we'll give that a mass of 5 kilograms. And they're lifting that box up 92 centimeters. Now, I'm using 92 centimeters only because that's like the standard height for like a countertop or something. It's probably a little bit low for a pickup truck. Probably depends on the make and model of your pickup truck. But this is a displacement, 0.92 meters. Now it happens to be, I'll just say up. Okay, so we're moving it up. I'm going to distance myself from reference frames right now, but I am making this thing go up. Now as it does that, there's an acceleration due to gravity of 9.81 meters per second squared that's acting down. But it says that it's moving at a constant rate. So what does that tell us about the acceleration of this box? 0, right? Constant velocity. So acceleration of the box equals 0 meters per second squared. So somehow gravity and the lifter are sort of counterbalancing each other here. And if I was going to draw a free body diagram, I'd say, okay, force applied by the lifter, force gravity, displacement, going like this. Notice I never attach my displacement to my force diagram. What I could say, if it's moving at a constant rate, if the acceleration is 0, I could say the magnitude of the applied force is going to be equal to the magnitude of Fg. That makes sense. It's all going to balance out. By the way, if I think about between F applied and delta D, what's the theta value?
0.
I'm going to ask you to start raising your hand more, okay? All right. Somebody with another raised hand. What's the angle between F applied and displacement? Come on. Yes, it is 0. They're collinear, right? That's the language we're using. They are collinear. So 0 degrees. I'm going to block that off just for layout. So the question was, how much work does the worker do? This person, they're just doing chores or something. So work done by, let's just call them a lifter. I don't want to have work of worker. Let's call it work of the lifter. They're going to have an applied force times displacement times cosine of theta. I know that the applied force is going to be really the magnitude of MAG, because the applied force is going to have to counterbalance the force due to gravity. I've got a displacement times cosine of theta. I'm going to start subbing in some values. So the mass, 5 kilograms. Remember, I don't have to put in the negative sign for the 9.81 meters per second squared because we're just dealing in magnitudes. Times the displacement, 0.92 meters. And then cosine of theta ends up being cosine of 0 degrees. And we've done this before. If you have a collinear situation, cosine of 0 is 1. Yeah. So I'm just going to jump to the 1 on that one. I'm not even going to type in cosine of 0. Somebody with a calculator, what do we get? What's the work done by this lifter? Yeah.
45.126 joules.
Nice. 45.126 joules. And if I was looking at sig figs, it's 3 sig figs, so approximately 45.1 joules. And we could write a little therefore statement for ourselves. Therefore, the worker does 45.1 joules of work. Seems weird to have the word worker and work in the same sentence. Maybe I should have stuck with lifter. Okay, so this is a collinear lifting situation. Now, the question might be, that's how much work was done by the worker, by the lifter, but how much work was done simultaneously by gravity? Because, of course, gravity was working against us while we were achieving this displacement. And this one's not so bad, except that I'm recognizing this is antilinear. They're opposite directions. And when the fact that it's antilinear means that I've got theta equal to 180 degrees. Notice that they're in opposite directions to each other, so 180 degrees. So if I want to figure out the work done by gravity in this situation, it's force due to gravity times displacement times cosine of theta. Well, I've already done some of the number calculations on this one, but it's mass times acceleration due to gravity, magnitude of, times the magnitude of the displacement, times the cosine of theta. And if I sub in my values, 5 kilograms times 9.81, displacement of 0.92, but the cosine of 180 degrees, I feel like we've been here. What's cosine of 180? Come on. Yeah, -1. All right. Got to give a chance for everybody to answer, okay? Otherwise, nobody answers but one person. All right. Now, the numbers are all the same except for that negative sign, so we say negative, and I'll plop it out there, 45.126 joules. In other words, that gravity is stealing energy. That's why we don't get up to speed, because this person's giving energy, and the gravity's taking it away. So the box is staying at a constant speed. It's not picking up speed. It's not gaining any more kinetic energy. So we can say that the work that's done by gravity is going to be equal to negative 45.1 joules. So therefore, the energy lost to gravity is 45.1 joules. Now, it's not really lost. It's actually kind of stored, and we'll come back to that later. It's stored as gravitational potential energy. And we talked about that previously, but we haven't really come back to it properly. I got a toy here. Oh, sorry, I won't take it off screen. People that are still writing. I got a toy here, and I want to push this toy. It's kind of a hefty toy, 1 kilogram. And just to put some context on what a kilogram looks like, this is an iron kilogram. Look, there's a cylinder, solid iron. It's got a bit of heft to it, right? So this is a serious toy. It's not like one of these little tiny Matchbox cars or something like that, right? This is a toy, you know? Like Grandpa used to give me to play with. So you got this 1 kilogram that's going to be pushed across a rough floor. So let's give ourselves a mass, 1.00 kilograms. And it's being pushed across the floor with 8 newtons of force. Looks like it's to the right according to the given there. So force applied is equal to 8.00 newtons. The toy's displacement is 5 meters, okay. And its displacement is 5 meters to the right as well. So we can throw that in there. The coefficient of kinetic friction, oh my goodness, mu k is equal to 0.50. And we want to know how much work is done by the kid. So the work done by the kid, that's going to be the force applied by the kid times the displacement times cosine theta. Now, if it helps to have a picture for this one, here's my picture. Kid's going this way. I've got a normal force. I've got gravity. Seems to me that I must have a force of kinetic friction, but I don't care about the kinetic friction in this part. I just want to know how much work the kid does. Notice I'm separating that out. How much work the kid does. The other thing that I remember is that I did have that unit graph for cosine curve. Remember, it looked like this, where this is 180, -1, this is 1, this is 0 degrees, this is 360 degrees. So I'm going to keep that in my mind as well. But when I go to calculate how much work is done by this kid, I can see I've got force due to the kid was the 8 newtons, times the displacement, which was 5.00 newtons, times cosine of, and when I look at this picture, the displacement is going this way. What's the angle between the force applied by the kid and the displacement? Yes? It is 0. Yeah, you can speak up. It's okay. Yeah. So theta is equal to 0 degrees because it's collinear again. I can see that it's collinear. Look, the displacement and the friction are pointing in the same direction. So cosine of 0 degrees, and my unit curve for the cosine function says that when 0 degrees is a theta, cosine is going to be 1, right? So again, oh, did I put it in newtons? I'm sorry. That's going to be 1. And this ends up being, sorry, my bad, meters. So I got 8 times 5. 8 times 5 is 40. 40.0 joules. And we can make a little therefore statement. Therefore, the kid does 40.0 joules of work on the toy. Now that's the kid. Maybe I want to know how much work was done by friction. And we played with a hockey puck before. We know that hockey pucks tend to lose their energy to the ice. In this case, what's going to happen to this toy? It's going to lose energy to friction, right? So let's make sure this is the case. Now, I already wrote my givens. I don't have to write my givens again. But if I'm thinking about that free body diagram, remember, we've got in mind that my force is going to the right. Sorry, my displacement is going to the right, and my kinetic friction is going to the left. That's not a free body diagram. That's just me keeping track of the vector directions. And so that means that the angle between them is how much? 180. And the buzzword we had was antilinear. Oops, not anti. Not uncle either. Antilinear. So they're opposite directions to each other. We know that the normal force and the gravitational force are going to cancel each other out. But we also know that I need to know that F normal is equal to Fg, at least in magnitude. The reason that's important is because we need to be able to calculate Fk, and Fk is equal to mu k times F normal. And so when I calculate that Fk, really it's mu k times the magnitude of mass times acceleration due to gravity. Again, we've kind of been there with the dynamics unit, so this isn't new information. But I can sub in my values, 0.50 times the mass, what did we say it was? 1 kilogram? Well, that's easy to multiply. Times 9.81 meters per second squared. And again, we've probably done enough 1/2 times 9.81s before. Isn't that 4.905? Hopefully that's shown up enough in the homework when we do like projectile problems and things like that. So 4.905 newtons of force due to friction. And it happens, based on my illustration before, it happens that it must be pointing in that direction. Look at that. My free body diagram sort of supports that idea. I come back over here and I say, okay, well, how much work is being done? I'll just use F for friction. I don't want to say kinetic friction because I'll get it mixed up with kid. You know, maybe I should have used child or something like that to not get myself mixed up. So I'm just going to say work done by friction. But that work done by friction is going to be Fk, where it's kinetic friction, I suppose, times displacement times cosine of theta. But as I plug in my values, I got 4.905 newtons times the displacement of, what was it, 5 meters, times cosine of, remember, antilinear, so 180 degrees. And again, based on that unit function for the cosine, that 180 degrees becomes what? -1. Yep. And I do my math, 5 times 4.905, I get 24 point... Can you guys check this on me? Did I get it all right there? What am I missing? Yep. Negative sign. Because the friction stole energy from me. It robbed the system of energy. This is energy loss. This is inefficiency. So then I can say, therefore, the toy loses 24, I could say approximately negative, how many, oh, there's only 2 sig figs in the mu k value. Approximately 25 joules. Loses 25 joules of energy to friction. And remember, I said before, you could say that the friction performed negative 25 joules of work on the toy. But a lot of people would rather hear that the toy lost 25 joules of energy to friction, right? And people say, well, what do you mean you lost energy to friction? Doesn't that mean, like, and you take your hands and you rub them together like this, and almost instantly you start to feel warmth, right? You know that when you lose energy to friction, that's being dissipated as heat. So we call this heat loss, right? We're not even talking about like what temperature the floor is or anything, but we still call it heat loss, okay? Because it's energy lost to that frictional force. Now, kind of a cap off to this could be find the total work done on the toy. Well, it seems to me that if you wanted to find the total work done by the toy, you talk about how much work was done by the kid and add that to the amount of work that was done by friction. And if I did that, I could go back and I could say, okay, well, the kid did 40 joules of work. Friction was, I'll get the unrounded value, negative 24.525 joules. And if I add that up, again, check my numbers. It can be around 15. I can see that. 475. Okay, 15.475 joules. And I got to go with the lowest number of decimal places here. Now, really and truly, if that 24 was going to round off to a 25, can you guys see that I would have to round this to a 24 and then I'd have to round this thing to a whole number? That's such a pain. That is a pain. It seems like we've lost something here. But it does end up being 15 joules, approximately. Because this guy's got to round off to the nearest whole number, which makes this the lowest number of decimal places, the lowest number of... you should round it because you should be recognizing that it's this value added to the other value. Because it's all kind of one problem, right? All right, so 15 joules total. Now, sometimes people, and I can say a little therefore statement, I could say therefore the total work done on the toy was 15 joules. Fine, fair enough. But then there are other people that are like so wrapped up in dynamics. Maybe this was like on an exam question or something like that. So I'm just going to do this little quick side note. Let's just say that there was like a part A, B, C or something on a dynamics problem where you were calculating the F net in one of these preceding parts, right? So you would say, all right, well, F net was equal to Fk plus F applied. And the Fk we just calculated was negative 24 point, oh no, that's not right. That's, the Fk we calculated was, if we make to the right positive, because dynamics you need a reference frame, and to the left negative, the Fk would be negative 4.905 newtons. And the F applied was 8 newtons. That's how hard the kid was pushing. And so the F net would be 3.095. And if I were to think about that F net acting on that box, and I would say, okay, well, what's the net work that's being done? Well, that would be F net times displacement times cosine of theta. I mean, doesn't the box still travel the 5 meters? So when I go to sub these values in, I say, okay, F net was 3.095 newtons times 5 meters times cosine of 0 degrees, because notice F net and the displacement are collinear with each other. So that's just going to produce cos of 0 is 1. And I do a quick little bit of math. Can somebody do this one for me? What's 3.095 times 5? I'd be shocked if it doesn't agree with what's going on over here on the left-hand side. 15.475? Nice. Joules. Approximately 15.5 joules. Oh, I guess it's going to be 15 joules again because there's a mu k embedded in there somewhere. All right. But like the nice thing about this is, even if this was on an exam question and you had done a bunch of dynamic stuff or kinematic stuff beforehand in parts A, B, and C, and in the end you calculated the net work, let's just call it, as opposed to the total work, it's the same thing. And it's nice to say that you can like follow different paths to the same answer, right? So that, I don't know if that doesn't really get us too much further in terms of concepts, but it makes it really clear that all these ideas play together on the same field.
All that we need to run